This is chapter 4, number 79. This is the first attempt at doing one of these by looking at the paper. So bear with me and we'll see how well this works, see if it's something we can do in the future. And just in case you don't have number 79 here, I'm going to set the problem all up from the beginning. It says a box is sliding up an incline that makes an angle of 15 degrees. So I'm going to put my 15 degrees there on my incline plane and draw a box. And it's sliding up, just to note the direction. And I'm going to go ahead and rotate my XY axis right away. And I'm going to use the traditional up and right as positive. So just as a reminder of that, up and right is positive. Coefficient of kinetic friction, so we do have friction, and it has a value of, the coefficient has a value of 0.180. Initial speed of the box, the bottom of the incline is 1.5 meters per second. And the question asks, how far does the box travel? So we're looking for, in my case, x minus x naught, how far up the incline it goes. So we're looking for that distance right there. We're going to lose the book now and focus on the paper. All right. And I might start with, since I'm looking for how far, the motion equation. So I'm going to list my 5 variables here. So we're going to have v final. And if it asks how far it goes before coming to a stop, we do know that v final is 0. And we don't know acceleration. 1, 2, 3, 4. And we don't know time. So we're stuck because for the 5 variables, we only know 1, 2. So what else can we do? Well, we have a picture here. We can draw a free body diagram. And hopefully, the link between this and our free body diagram will be acceleration. So hopefully, we'll be able to figure out our acceleration. So let's go ahead and draw the free body diagram for this block that is sliding up the incline, slowing down. It's going to come to a stop. So we will have normal force, force of the weight. And since it's moving up the incline, we'll have force of friction, kinetic, down. And that's it. Okay. We'll start summing our forces. So let's sum the force in the x direction equal to max. And let's go ahead, we're probably going to need it. Let's sum the force in the y direction. It'll be 0 because this is moving up and down the incline like this. There is an acceleration, but it's not like jumping up off. Okay, so it's not going any movement at all in the y direction. That's why this acceleration right here is 0. How many forces are there in the x direction? Well, if we think about our x-axis here, we've got friction and an x component of the weight. I'm going to put the signs on. So negative force of friction kinetic, negative force of weight in the x, taking care of the signs because they're both going to go down the incline, equals max. And we have not enough information, right? It looks like we're stuck because we can't get weight in the x because they didn't tell us mass. But I'm going to keep going with the assumption that masses will eventually cancel. That's what I'm hoping to happen. So I'm stuck here, but let's go ahead and plug in some more. Negative force of friction kinetic minus mg. Inclined plane problem, we're getting the x component, and it's set up like this. We'll use sine. So sine of 15 degrees equals max. And nope, the m's don't cancel yet because I don't have an m in here currently. So let's look at the y direction. Normal force plus weight in the y, or excuse me, normal force minus weight in the y. Forgot to put the sign on. Physics habit. AP Physics, we put the sign on as we're writing the variables. And here we have an expression for normal force. Great, but that doesn't solve my problem here. So I'm going to go ahead and somewhere write the equation for friction. Force of friction kinetic equals mu sub k times the normal. And now we're getting somewhere. So I can put in for force of friction mu sub k and the weight in the y, which will be mg, the entire weight. And if I use sine for the x component, for the y component, I will use cosine of 15 degrees. Now I can put this in down here, and I've already taken care of the sign. Remember, your equation for friction right here is magnitude only. That's magnitude only. But I've already taken care of the sign. So we can plug that right in. Let's do that. So negative mu sub s mg cosine of 15 degrees minus mg sine 15 degrees equals max. These were indeed x's. Make that real clear. Those were x's. And now good news. We have m on both sides of the equation every term. So you could factor it out to prove it. But if it's in everything, it's going to cancel. It's got to be in everything. So goodbye m's. That's a good thing. Continuing on here. G is something we know. Mu is something we know, and cosine and sine is something we know. So we're home free. We can get the acceleration from this, and I'll plug this in. So we've got negative 0.180 times 9.8 meters per second squared, cosine of 15 minus 9.8 meters per second squared times the sine of 15. And now I got to grab my calculator here. Okay, so let's see here. We got 0.18, and don't worry, I'll take care of the signs. 0.18 times 9.8 times cosine of 15, and uh-oh, that shouldn't have happened. We were in radians. There we go. Let's try that again. 0.18 times 9.8 times cosine of 15. We have negative 1.7, and 9.8 times sine of 15. Oops. So minus 2.54, call it that, equals acceleration. And these should have units of meters per second squared, because sine and cosine don't, these are degrees, they're not units. So we have still meters per second squared. So we should get, using my rounded numbers here, 1.7 plus 2.54. They're both negative, so it'll be a negative 3.94 meters per second squared. Let's make sure that makes some sense. Our block is moving up the hill and slowing down. So while the velocity is up the hill, the acceleration should be down the hill. And that makes sense. Negative means down the hill. So that works out. Now we go back, and since we have negative 3.94 meters per second squared, I'm going to pick a motion equation and go from there. Let's see. I'm looking for displacement. Let's try this one. X minus x naught equals v naught t plus 1/2 a t squared. No, don't pick that one. That'll get us time, which I don't think we were solving for. We're looking for displacement, yeah. So v final squared equals v naught squared plus 2a, there we go, y minus, or x minus x naught. So our v final is 0. Our v initial, 1.5 meters per second squared plus 2 times negative 3.94 meters per second squared. And then you guys can do some algebra. I'm running out of paper here. I'm going to skip some steps and do this on my calculator. If you don't like the way I do it on my calculator, that's okay. Do it your own way. 1.5 squared. And then I'm going to divide by 2 times 3.94. And then I'll pick a sign. Let's see. So this will be a negative divided by a negative. So we'll get a positive 0.2, about 0.29 meters. Let's go check the key. See if this was all for naught. 79. Hey! The key got 0.265 meters. We're close. Let's see here if they got the same set of trig functions. I think it's probably just in the squaring because they do have 1.5 squared. And yeah, pretty sure it's just in the squaring. I'll double check. I won't actually post this unless this is correct. But that should work for 0.29 meters. The book does something that you should never do. The key here, don't do this. Okay, this is not a free body diagram. If this helps you solve a problem, great, but you should still draw your free body diagram. If you're breaking things into their components, that's an extra diagram that does not count as the free body diagram. That concludes the sample problem.